I promise you, the molecular orbital theory of bonding is the last one we're going to study. It's the more recent one. Okay? Remember that we were talking in the previous video about how oxygen is a non-polar molecule, but it orients itself in an electrical or a magnetic field, which didn't make any sense and could not be explained by any of the two previous models. Here you have oxygen again, the Lewis structure. You can set the difference in electronegativity between the two oxygens is 0, so it should be pure covalent bond. There's two lone pairs of electrons. There's no reason why an electrical field would cause oxygen to orient itself. Okay? Oxygen is not magnetic, but is attracted to magnetic fields. And this is what we're trying to explain. Now, we call this paramagnetism. When you have a molecule that should not be attracted by a magnetic field, but it does, we call that paramagnetism. Usually paramagnetic molecules have unpaired electrons. That explains why they're attracted by a magnetic field, but this is what we're talking about. Oxygen doesn't have no unpaired electrons, so how do you explain this? But the way, when all of the electrons are paired, we call that a diamagnetic, and either it doesn't respond to magnetic fields like nitrogen, or sometimes there's a very weak repulsion. Let's just leave it at they don't respond, they don't orient themselves. Okay? But you can say, well, that's easy. Unpaired electrons attracted, paired electrons not attracted. How about oxygen? So we need another theory. So the molecular orbital theory is going to distribute the electrons in the molecules very similar to how we did it in the atoms, but this time instead of atomic orbitals, we're going to be talking about molecular orbitals. A molecular orbital is a region of space in which you can find a valence electron. But this time it covers more than just an atom in there, and it's again represented by a wave function. And a molecular orbital is also full when it contains two electrons with opposite spin. So far, other than this, at the molecular level, you don't see no difference in here. Now, when you combine or when you overlap two atomic orbitals to form a molecular orbital, remember that there was two solutions to the Schrödinger equation. They had different signs. So that's in phase means when you are adding two equations that have either positive or negative sign. And when we talk about out of phase is when you're combining a positive with a negative. But basically, without getting too much complications, you can produce two different kinds of orbitals. You have a lower energy molecular orbital and a higher energy molecular orbital that we represent with a star, so everybody knows that's a high energy. In the low energy, most of the electron density is between the nuclei, so they hold the nuclei together, and we call them bonding orbitals. Again, because, and we're not going to get into the mathematics of the Schrödinger equation and things like that, but when you go to the high energy molecular, the highest density is going to be away from the nuclei. So they don't hold the nuclei together, we call them anti-bonding. And when we are filling out the molecular orbital with electrons, we are going to follow the Aufbau principle. So once again, we fill the lowest energy first, and then we'll move upward. So let's look at an example. Here you have two s orbitals. When they combine, they form two molecular orbitals. Since they're an s and an s, they're going to be sigma, or sigma s. Okay, sigma because it's a collision, and the anti-bonding is going to have that star. You have a bonding, low energy, and anti-bonding with high energy. Notice that the bonding has the electron density between, the anti-bonding is away from the two nuclei. There. What if you do p orbitals? Well, these are still going to be sigma because it's head-on collision. That's what we call a sigma p. But you're going to form a bonding and a non-bonding. The bonding is lower energy, and it's called bonding because it holds the two atoms together, the two nuclei together. High energy, you have the anti-bonding with the star, and see that the electron density is away, so that does not hold the nuclei together. Now, if they interact sideways, they're going to form pi orbitals. But once again, you form two. You form a pi bonding and a pi anti-bonding. The pi bonding has lower energy than the pi anti-bonding. So we represent all of that with a molecular orbital diagram. And the explanation may seem confusing, but we'll look at examples. We are going to represent the orbitals with horizontal lines. We try to use dashed lines to show you which atomic orbitals combine together to form a molecular orbital. We always have bonding and anti-bonding, and remember the bonding is always going to be lower energy, and we fill them the same way we fill atomic orbitals by the Aufbau principle. Because it's already kind of complicated, we are going to use only the valence electrons, because they're the ones who form the bond anyhow, but that saves you from having to also mess with the core electrons. So hydrogen, because that's very easy, is 1s1. So you have here the two hydrogens, that's going to form a 1s bonding, 1s anti-bonding. These are sigma, because they're s orbitals. You have 1, 2 electrons, so they both fit into the bonding orbital. So hydrogen forms a very stable molecule, because all of the electrons are forming a bond. And noise is more stable than the atom, because the energy of the bonding is lower than the energy of the individual atoms. So far, so good. Now, for bigger atoms, we are going to define bond order to represent how many of the electrons actually go into bonding or anti-bonding orbitals, because the more bonding electrons you have, the stronger the bond is going to be. Okay? So this is one of those hypothetical numbers that doesn't really exist, but bond order is the number of bonding electrons minus the number of anti-bonding divided by 2. It's kind of like an average, except that you subtract instead of adding. Okay? So the higher the bond order, the stronger the atom is. If you end up with a bond order of 0, that means the molecule does not form. You don't have a bond. The strength will be 0. So there's no bond in there. So let's look at another molecule, helium. Helium has 2 electrons in the 1s orbital. So once again, there's s orbitals, so they form sigma. You have sigma bonding, sigma anti-bonding. This time we have 4 electrons, 1, 2, 3, 4. Okay. The problem is, when you look at the bond order, you say it's the number of bonding. How many bonding do I have? 2. Minus the number of anti-bonding, 2 divided by 2, that's 0. The bond order is 0. Yeah, but you remember, helium is a noble gas. It does not form molecules. So once again, this theory explains why helium does not form an atomic molecule, because the bond order will be 0. That means there's no bond. The 2 helium atoms are going to separate. Isn't that neat? So this, unfortunately, is something you're going to have to memorize. How do you do molecular orbital diagrams, and the order of the sigma and pi when you're combining the p orbitals, the bonding, the molecular orbitals, the order in which they appear, they have been determined experimentally. Okay, you can do it mathematically, but most of these have been determined experimentally, which means there's only one thing to do. You have 2 different sets of diagrams, and you just have to memorize them. Okay? So when the atom is either oxygen or to the right of oxygen, this is what you use. The 2 S's are always going to do the same thing. But noticing here, we begin with the sigma bonding, then you have the pi bonding, then you have the pi anti-bonding, then the sigma anti-bonding. If the atom is to the left of the oxygen, we said that it's not going to cause any trouble, but when the P combine, you're going to have pi bonding, then sigma bonding, then pi antibonding, then sigma antibonding. And like I said, you just have to memorize it. Okay? There's no way around it. But you're going to be given usually the atomic molecule, you put the electrons where the atoms are, and then fill this up and see what happens. So let's do an example. Okay? We are going to be doing oxygen. Okay? So we know oxygen is 1s2, but we don't put in there 2s2, 2p4. So we have two oxygens. Because it's oxygen, we're going to have the sigma bonding, pi antibonding, sigma antibonding. So the 2s we have 4, we fill that, no problem. Now we have 4 and 4 electrons, so 2, 4, 6. Oh, the pi antibonding, you have to separate them. There's two things that are interesting about that. One is, what is the bond order? Because they were asking you, calculate the bond order. Okay, how many bonding do we have? 2, 4, 6, 8. How many antibonding? 2, 3, 4. Divided by 2 is 2. Remember when we did it for hydrogen, it was 1. Because oxygen has a double bond that's stronger than the single bond in hydrogen, right? So the bond order is higher. But the most important thing is, look, we have 2 ampere electrons that we didn't see in the Lewis structure. But when we use this model, we have 2 ampere electrons. That explains the paramagnetism. That's why oxygen orients itself in a magnetic field. If you don't believe me, try nitrogen, try number of others, and you will see the difference. Okay? The last thing I'm going to talk is about the band theory. Whenever you talk about solids, the molecular orbitals are so close together that they're considered bands. So you have a bonding band or valence band and a conducting. Basically, what they're saying is the valence band is the lower in energy and the electrons are held in place. The conduction band, the electrons high in energy, and they're attached very loosely. Remember, they're not caught between the two nuclei, so they can move. Okay? So what type of solid you have is going to depend on the distance, the gap between the valence and the conductive band. Whenever they're very, very close, it's very easy for an electron to jump from the valence to the conductive, and then that electron is free to go anywhere. That's like getting to the interstate. So a conductor has a very small gap, and these electrons can move. It conducts electricity very, very well. If the band is real big, this electron may try to jump, but it can't because of the distance. So the electron never gets into the conductive gap. It does not conduct electricity. That's an insulator. When the distance is so, then some electrons may be able to jump, some won't. So it conducts a little bit, is better than the insulator, but not as good as a conductor, so you got semiconductor. Once again, this theory can explain that too. I know this is starting to get complicated, and especially, in my experience, you need practice doing molecular orbital diagrams. I've told you that before. I have worksheets that you can do. Practice makes perfect. Okay? So, if you go to my Watson profile, or to the description, click on the Watson profile. If you make an appointment, not only I can answer your questions, but I can let you use some of my worksheets where you practice. It is really not difficult. Once you do it 3 or 4 times, yes, all of a sudden you realize, oh no, it wasn't so bad. But you need practice, okay? And that's what you can get by going to Ysant.